So we stopped last time discussing the Gaudin model. So I would like to recall. And we will discuss some properties of the system which are similar to those of the Tode system, and there are some new systems, new properties which we have not faced before. So it is defined with the help of the Lux operator, which is a matrix, which is now a rational function on parameter z, zi, with the residues, which are matrices. And these matrices are matrices with values which are functions on our phase space. KL, E, KL, with the number I. So it means that our manifold is just the the sum of JLN double with the number I from 1 to big N. So here I is from 1 to big N. And the entries of the residue of the Lux operator at a point Zi are functions on the eth copy of this dual space to the Lie algebra JLN. Okay, and so we consider this this linear space with the natural Poisson bracket, which is the Lie Poisson bracket on each component, and with commutative relation between functions on different components of this copy of the Lie algebra, or the dual space to the Lie algebra. Lie Poisson bracket, a natural object on this phase space. And first statement was that the Poisson bracket in terms of the entire Lux operator can be represented in the following form: R U minus V L U 1 plus LZ1 it's 1 LU. Yes, and the R matrix here is also a rational function, which is called the Young R matrix. U, there P is our famous transposition operator.
C minus U.
Yes. Thank you very much. Thank you. Yes, that's right. This form of the Poisson bracket was for us the key to the construction of an integrable system. So we stated that it was the theorem that traces of L now the power S of Z, which is E S of Z. So all this set of functions on Z are so each function from this set represent a generating function of integrals of motion. So the statement was that ES Z commute, Poisson commute with ETU. And it means that if we consider coefficients of these rational functions, so IS of Z, so we consider the trace of the power of this rational matrix, it will be rational function on Z, which has Laurent decomposition at the point that I 1 over Z minus Zi power S with some, I don't know, the first plus lower terms. But all the coefficients of this decomposition at the poles are integrals of motion. So this is the statement that these functions commute, Poisson commute for all values of parameters, and it means that if you decompose this function at all poles. I'm sorry, there is also number I 0, but there are other terms here. So all this set of J is an involutive family, is an involutive family. So this was the powerful characteristic feature of this representation. So I mean that we represent the Lux operator depending on the parameter, and we have the Poisson bracket also depending on the parameters. So it produces a huge family of involutive functions. So this was the idea. And we started to discuss the spectral curve. Spectral curve. So it is the characteristic polynomial of the Lux operator. So I would like to that it is some curve in R2, but it's better to look at this picture on the projective space, or even better in the projectivization of the canonical bundle to some rational surface. But okay, so the simplest way to look just on the equation, which is chi of L of Z depending on lambda, which is the determinant of L of Z minus lambda E. And this curve is defined by Lz of lambda equal 0. So the open part of this of the projective curve is given just by this equation on the two-dimensional space. And many of the algebraic geometric properties of this curve are intrinsically important for the integrability. So we will discuss some issues of this fact. Now I will consider the specialization of this model, which was originally invented by Gaudin, which is the Gaudin model for SL2. So the GL2 specialization is obvious, but the SL2 needs to consider just the invariant, the common, the common level of Casimir functions. Okay, in GL2, you remember that the trace C1, which is E11 plus E22, is the central element of S point GL2. So we can consider the common level subvariety of all these Casimir functions in all copies of our Lie algebra GL2. And it means, and the subvariety C1I equals 0. So we can consider just the matrices, the Lux matrix with the zero trace. Okay. And in this case, I will use the notation that L of Z, which is now the 2 by 2 matrix, it is equal A of Z, B of Z, C of Z, and minus A of Z. A of Z is H, E, F, H. It is equal the sum of H I Z minus Z I. B of Z is the sum E I Z minus Z I. And C of Z is the sum F I Z minus Z I. There E I, F I, and H I are generators of the eth copy of SL2. So the commutation relation between these generators are known, but I will write HI with EJ is equal to delta function IJ EJ. HI Fj is minus delta IJ Fj, and EI Fj is equal to delta function Hi. So am I right? Maybe not. No. Obviously, like this. So it means that H is represented by the matrix minus 1. E is represented by the matrix like this, and F is such matrix. This is the standard basis of SL2, and these are relations. And also we suppose that there are several copies of SL2. Different copies commute between themselves, and inside one copy we had the standard SL2 commutation relation. Okay. We also considered the the spectral curve for this Lux operator. So our spectral curve L of Z minus L dot E, and it is equal lambda square minus the determinant, plus determinant, but the determinant is a square of Z minus B of Z, C of Z. Okay. So it means, for example, that this is the hyperelliptic curve. A hyper curve. So now we will discuss some new concept, which is very famous in integrable systems. So it is very related with the action angle variables, and it is called the separation of variables. And first of all, I would like you recall what is the action angle variables in integrable systems due to the Liouville theorem. Okay, I will repeat. So the Liouville theorem says that if we have a symplectic manifold of dimension 2n and a family of integrals dependent integrals in involution, then for quite a general level set, omega h, which is the level set M from X, such that hi of X is equal hi of X, a level set of integrals so quite a general level set of these integrals is a torus, is a Lagrangian torus. So it is the subvariety of dimension n, which is Lagrangian with respect to the symplectic form. And moreover, so this is the point, this is a torus, and at the neighborhood of this point, so the neighborhood, even the tubular neighborhood of this point can be represented as the product of Rn of S1 n times. So this is the torus, and the tubular neighborhood of this point can be represented as just the direct product of some open set in Rn multiplied by the torus. So it's a fibration by Lagrangian tori. And one can introduce very good variables in this space. So the variables ei and phi I, which are called action angle variables. variables. The properties of these variables are that they could be reconstructed in quadratures, so it's quite not explicit, but it is different from the chaotic dynamic in any sense. It can be reconstructed by quadratures, and the symplectic form, so they are canonical coordinates for the symplectic form. And these functions are they depend only on integrals, are functions only on h, j, on this set of integrals. So these functions are constant along the terrae, which represent the evolution of the system. And they're conjugated, so this is some another choice of integrals of motion. And the dynamics with respect to this I is just canonical. So if we see the time ti is the time corresponding to hi, then d phi j with respect to d ti is just a delta function. So it means that these coordinates are just times with respect to this choice of functions. So if we re-express the Hamiltonians by these new variables, we will get some linear combinations of this equation, and it means that they are also separated variables. So the equation of motion in terms of angle variables can be treated separately. It is very simple, but most important thing for us now is that they reduce us to separated differential equation on each direction ti. Now we will discuss another appearance of separated variables in the Gaudin model, in the SL2 Gaudin model, and it is very geometrical. So let us consider L. I need some notations from this model. So L of z is a z bz c of z minus e of z. First of all, I'd like to write the Poisson bracket between entries of our Lux operator. So my statement is lemma that A of z with B of z is B of u is 1 over z minus u A of z minus B of z minus B of u, yes, A of z with C of u is equal minus I have some doubts. Yeah, I will verify now. And else we need 2 and here and b of z with c of u is equal 1 z minus u a of z minus a of u. Sorry. Okay, let us calculate this a of z with b of u. We have calculated very similar bracket in previous lecture. So it is the Poisson bracket of h I z minus z I sum over I with the sum over j e j u minus z I z j. Sorry. And this is the sum over I and j on z z I u z j h I e j, which is delta function of I and j multiplied by 2 ei. So this means that we can omit one of the summation and to take j equal I. So it is the sum over I z minus z I u minus z I, and here we have 2 e I. And now we have to replace this expression. So it is equal the sum over I 2 ei 1 over u z minus u, and here it will be 1 u z I minus 1 over z minus z I. Do you agree? Okay. And it means that it is 2 over z minus u, sum of ei u minus z I minus sum over I ei z minus z I. And it means that it is 2 over z minus u b of u minus b of z. So my mistake is only in sign. So here there is sign minus, here the sign plus, and let us verify this formula. B u c u I'm sorry, bz c u. The sum over I ei z I sum over j f j u minus z j. We always can take the delta function, so I will consider v on the summation on I, and it is the bracket ei fi divided by z minus z I u minus z I, and this is the same expression, 1 over 1 over z minus u. And here I have hi, the sum of hi u minus zi minus sum of hi z minus zi. So it is also the opposite sign here. Now I will introduce new variables on the phase space of our system. And new variables will be the following. So the function c of z is the sum of fi z minus zi from 1 to n. I will consider the zeros of this rational function. So you understand that it is it is some polynomial, some p of z, which is some polynomial p of z divided by the product of z minus zi from 1 to n, and this is the polynomial of order n minus 1. Okay, and I would like to consider the zeros of this polynomial. So it is c c0, and there are some j from 1 to n minus 1 y j no, sorry, z minus yj. And here we have the product I to n z minus zi. Okay?
Is this something need to be proved?
I consider the sum of such rational functions. So it's a rational function of degree minus 1. So if I collect all the denominators in the denominator, so here I get the polynomial of degree n minus 1. Does it need to be proved? No.
So you just expand it?
Yes, just expand. So, but in the contrast to the poles, which are just constants. So we consider the Lax operator, which is the rational function with fixed poles. So the poles of these rational functions are constant, but the roots, the zeros, are some dynamical variables. Okay, so many variables are roots, are zeros of the function z. So let us consider zeros of c of z yj. They are dynamical variables. It means that they evolve in some manner. The poles are constant, but the zeros are dynamical variables. And we consider the partners of these variables. We introduce omega j, which is a of yj. Okay. So now we consider the variables on our phase space, which is the set of I, j, and wj, and j from 1 to n minus 1. remark. The point Pj with coordinates yj and wj in R2 lies on C, on the spectral curve. So this is some spectral curve, hyperelliptic spectral curve, and the points evolve along this spectral curve. Why it is true? Let us verify. What we have to verify, that if y and w such that y is 0 of the function c and y is the value of the function a at this point, then the equation is satisfied. It means that the characteristic polynomial of lambda z, not z, but y g of wg is 0. But if we substitute z by y of g, we have c equals 0, and then they substitute lambda by w, which is the value of a. So in this case, we get that a of yj square minus a square 0. Is it clear?
We have another letter for a spectral curve.
Another, yes, of course, gamma. It is also the standard letter for the spectral curve. So here I designed the complex version of this curve, but this equation defines the real spectral curve and the complex completion. Okay, and these variables are very special. So they are separated in the following sense. We will need these brackets. Lemma. So you see on our phase space we have chosen another variables which are dynamical. Each pair of variables define a point on the spectral curve, and okay, the next step will be manifestation of the very particular properties. So lemma is the following, that they are canonical variables for our symplectic structure. So the Poisson structure of yj is just delta ij. So let us verify. First of all, it is quite evident that the brackets between variables y are trivial. Do remember that C C of I is 0, so I is a function, so it's the root of an equation, so it's a function on the coefficients of this equation. Okay? It doesn't depend on other variables, so it depends only on coefficients of C. And the coefficients of C commute between themselves. Okay? You remember that C of Z is the sum of EI, Z minus Zi, and these are the E generators of different copies of SL2. They commute between themselves. Okay? So the roots of this equation are functions on the coefficients. So if the coefficients commute, the roots commutes too. Okay? The more complicated calculation is is the bracket between different variables, but how to do it? Okay, I will represent C of Z as, okay, C of Z. Now I have to calculate A of Y I with Yj. So this is the part of the statement, so it should be delta ij. You see, I mean that this is the canonical variables. All other Poisson brackets are trivial. Let me write it. Omega I, omega j is 0, and yi with ij is also 0. So we have demonstrated the first simple part of this statement. Next one is this. So how to calculate the such a bracket? Let me write that it is the A of Z is the sum of HI Z minus ZI. So A of YI is the sum of H J YI minus ZJ. So, and then I try to calculate this bracket. I have to do the following thing. It is D by the, if I differentiate A, so there are Poisson bracket between ij with this y and with yj with the coefficient h. Okay, so I will write and then we will discuss it. Z of yj with z equal yi plus A prime of y j I'm sorry, I y yj. Do you need some comments? Okay, so we try to calculate the Poisson bracket of this expression with yj. Okay. Of this expression with yj. there are two parts. First of all, we can consider the Poisson bracket of the coefficient hk with yj. And it is the same as to calculate the Poisson bracket of the function a of z with yj, and then put the value yi in place of z. So when we calculate the Poisson bracket of yj with hk, okay? But then when we calculate the bracket with y variable y, we do it just by the Leibniz rule. So we consider the derivative with respect to this variable and then calculate the Poisson bracket. But we know that this is 0. That's why it is just this formula. Let us remember it. Let us recall this expression. The bracket of a z with c u, but in this form. So I'd like to write it like this, zi. And now we have such a formula, yj. Let us apply z. No. Here we have u, and here u. Let us apply the Leibniz rule to the product of elementary polynomials. So it is c z p u minus zi, and here we have the Poisson brackets, the sum of Poisson brackets of a z with yj of p u yj divided by j. Maybe minus, and I will rearrange this expression. It is minus c0 p k u minus yk u minus zi, and here there is a sum over j a z yj divided by u minus yj. So it means that a yi with c of u is minus, so it is just c of u minus c of u, and here we have the sum over j, the sum over j of bracket a of yi with ij divided by u minus yj. So I'd like to compare this Poisson bracket with the residue of this bracket at the point yj. So the resulting step was to compare this calculation with the bracket which we know, this bracket. So this expression. And now we see that this expression, this residue. So it means that we calculate this expression and then consider residues of this expression with respect to the variable u. And there are residues at yj. You see? And this residue is exactly the value of this bracket which we calculate. But from this formula, we know that this expression is the same as this expression. And it has residue only at yi. Doesn't have residues in other points y. Means that the only non-trivial bracket is if I equal j. And the values also coincide. So if we calculate the residue, we have to put here yj, and it is the coefficients here, the same coefficients here. Okay, so this is the demonstration that of this part of the statement. Let us calculate the last part that the values, where are the values? So yi are the zeros of the function c, and wi are values of the function a at the points yi. Let us now calculate the brackets of a of yi and a of yj, and we will do it by the same techniques. So it should be the bracket of a of z with a of u if we then substitute yi in the place of z and yj in the place of u plus different terms. So it is a prime of a in yi with yi and a of yj plus a of yi yj a prime of yj, and the last term is a prime yi I'm sorry, plus a prime yj yi and yj. So the method is the same. So we have the function; those coefficients depend are dynamical variables, so they have some non-trivial Poisson bracket. But now, as an argument of this function, we also consider a dynamical function. So when we calculate Poisson bracket of such complex aggregates, we have to consider them separately. So firstly, I consider the Poisson bracket between coefficients of these functions. So it means that I calculate this Poisson bracket as a function of independent, non-dynamical variables, and then substitute the dynamical variables. And then I calculate the Poisson bracket between the value and the coefficients of other function. It is this expression. Then inversely, the value of the second function with the coefficients of the first function, and then between just the values. But all these Poisson brackets are zeros, and this is zero because of the commutation relation of the coefficients of our Lax operator. So this is the demonstration of the statement. So it means that the new variables which correspond to the points of our hyperelliptic curve P1, P2, etc. Let us realize a little bit what happens. You see this equation, this curve is given by this equation. How to say? So it is lambda square plus the determinant of L of z, and this is a rational function on z. This is just the determinant of our Lax operator. The fact that it is traceless gives this minus. Okay. So it's just a characteristic polynomial of our Lax operator. If you remember how we introduced Hamiltonians, they were the spectral invariants of this matrix expanded at the poles. Remember, before we considered traces of Lk of z, and we expanded them at the poles of z. So around z minus zi, it evolves like it has such a Laurent expansion with some Ak I 0 plus z minus zi k minus 1 k I 1, etc. And all the set of this coefficient were in involution. Now we can consider the coefficients of this characteristic polynomial. They are also rational functions on z. So it is lambda square plus sum of h I 2 z minus zi square plus the sum of h I 1 z minus zi of the first order. And that's all. That's all. So the non-trivial Gaudin Hamiltonians are these functions. H1 are central if I am right, but it is not now important. So now we consider the coefficients of this characteristic polynomial. Remark h I k is basis in the ring of spectral invariance. Of L of Z. It was the part of your home task and of the last lecture that in place of considering traces of powers, we can consider the coefficients of the characteristic polynomial. It is just another basis in the same space of functions. Is it approximately clear? So my principal statement that the spectral curve itself is an integral of motion. Different choices of levels of Hamiltonians change the spectral curve, obviously. So if we change this coefficient, so we change traces of powers of the Lux operator, but it can be re-expressed as a change of coefficients of this of these Hamiltonians. So the statement that the coefficients of the characteristic polynomials is another basis in the ring of integrals of the Gaudin model. Is another basis in the ring of spectral invariance integrals of the Gaudin model. The spectral curve itself is an integral of motion. So it means that it doesn't change along the Hamiltonian flows of our system. And now we found some new variables which correspond to the coordinate of points in R2, which are points of this spectral curve. And it means that they should evolve along this curve. If we turn on the dynamics, the evolution, the Hamiltonian evolution, this point evolve around this curve. Okay? Because the curve itself doesn't change along the Hamiltonian flows. Okay? And we are very close to the concept of separation of variables. So I would like to demonstrate the following statement, that the problem of solving this Hamiltonian system separates into different points. So they evolve independently. Each point evolves independently along the Hamiltonian flows. So to solve the system, we have to solve the two-dimensional problem. But to illustrate this, I need such a notion as a canonical transformation. We haven't discussed it, but it is very basic notion in symplectic geometry and Poisson geometry and integrable systems. We will briefly discuss this. Canonical transformations. Let us remind what is the standard Poisson bracket, Pi dqi, I, the standard Poisson and symplectic variety. So if such a structure is given, the very natural mathematical question, what type of transformations preserve this structure? What are the symplectic diffeomorphisms or symplectomorphisms which preserve such a structure? It means that locally, how to find another coordinates. I will denote it by big pi and big qi, such that they are functions depending on pi and qi, such that the Poisson brackets are also standard, and other Poisson brackets j qi qj is equal 0. And suppose that such a structure exists, one introduces the so-called generating function of this transformation. S is called generating function of such a transformation if it is a function of a very strange set of coordinates of pi and pi. So it is a function on the same halves of the coordinates, and ds of dpi if is qi and ds of dpj is minus qj. Have you heard about this? So it is quite a standard method in Lagrangian approach in Legendrian transformations, but it has also in interpretation as the symplectomorphism or Poisson diffeomorphism. Okay, and it is a very it has a very simple interpretation. So if we have two such type of coordinates, let us consider a differential one form, which is the sum of pi dqi. As I have written, it is different. Qi dpi. And if it is a symplectomorphism, no. I would like to write the following thing. It is the first form, and the second one form, lambda 2, is the sum of qi dpi. The fact that it is a symplectomorphism says that d lambda 1 is equal to d lambda 2. Do you remember how to calculate the differential of the one form? So d lambda 1 is just the sum of dqi dpi, and d lambda 2 is the sum of dqi dpi. if it is the same symplectic form, then, so if it equals, then it means that d lambda 1 minus lambda 2 is 0, and over R to n it means that it is a closed closed to form, and it means that it is exact form. So it means that there is some function s such that exists some function s such that lambda 1 minus lambda 2 is just ds. And what it gives the following, that the sum of qi dpi minus sum of qi dpi is just ds. So if we express this function in terms of s, in terms of coordinates p in small p and big P, then is differential just the sum of ds dpi dpi plus ds dpi dpi, and by comparing these expressions we get the definition of the generating function of the canonical transformation. It means that ds dpi is equal qi, and ds dpi is equal minus qi. Returning to our exploring of separated variables in the in the SL2 Gaudin model, we could state the problem. Let us find a canonical transformation for the SL2 Gaudin model from y I omega I coordinates to the action angle ones. I and I. So you see, both of these coordinates are canonical coordinate on the Poisson manifold. So we can ask ourselves to find the canonical transformation, generating function on which describe this transformation. So there is some function on yi and I of all these such that ds dy I is omega I, and ds di I is the phi I coordinate.
Capital is the corresponding canonical momentum?
Canonical action variables.
What?
Canonical action variables.
Yeah, but is it the corresponding to y?
No, they're different variables.
No, but I mean it's the corresponding canonical momentum for setting S.
Canonical momentum. The derivatives. Yes, of course.
Yes,
of course.
Set S, you have to set a variable dependence.
Yeah.
You need or two coordinates or a coordinate.
Yes, I think you're right. Yeah. So, in the lemma says that such a canonical transformation, the generating function of this canonical transformation, can be represented as the sum of s. Let me write small s of yj of all I over j. And this function solved the following there. S of y and all the set of action variables solves the following equation. So I need the expression for this. So it's a polynomial on z, lambda, and all action variables, all Hamiltonians. See, it is the same as lambda square plus the determinant of L of z. So this small s solve the following equation. P of s s, just a moment, of z and ds over dz, depending on all other variables and I, is equal to 0. Okay, it's the statement. I suppose we will prove it later, today or maybe next Monday.